Hello to everybody. The title of today's presentation is Risk Area Zoning using a new 3D seismic refraction technique in the gas pipeline right-of-way of a gas and condensate field in the Peruvian jungle. As introduction, a 3D seismic refraction technique applied over the gathers of a 3D reflection seismic campaign combined with the high-density lidar digital terrain model, or DTM, topographic information will result in the creation of a 3D P-wave velocity model around the right-of-way, or DDB, of an hydrocarbon gathering pipeline system called U200. The P-wave velocity variation along the right-of-way of the pipeline will be correlated with geological and geotechnical behavior of the soil. The pipeline is approximately 14.4 kilometers long per 1.5 kilometers wide of area of influence and is located in the complex Peruvian jungle. The soils surrounding the pipeline system are affected by rainfall, drastic topographic variations, presence of groundwater, lithological changes, and other structural factors that highly affects its stability. Preventive maintenance of the pipeline is currently considered as a critical activity during the field life in order to avoid any geodynamic risk like major landslides that could affect its integrity. The study has included a processing of field seismic gathers data in conjunction with LIDAR DTM topographic information, with which a 3D model of P-wave velocities was constructed, a calibration of the P-wave velocity model with field data, and an interpretation of the final P-wave velocity model. Let's go now with the methodology of the study. Seismic refraction is a widely used and applied geophysical technique in the geodynamic characterization of soils. The methodology of a 3D seismic refraction study consisted of selecting the seismic gathers of receivers and sources located around the pipeline, in which a previous geometric divergence compensation is applied. In these gathers, the first arrivals of seismic P waves are picked, representing the time it takes for the waves to travel from source to a receiver. These measured times then go through several iterations of tomographic inversions, which consist of varying the velocities within the cells of a three-dimensional grid, until the calculated times are very close to the measured ones. This procedure will result then in a 3D model of the P-wave velocity. This is the high-density LIDAR digital terrain model topographic information that has been also used to build a P-wave velocity model around the pipeline. At the left of the slide, you will see all the points clouds returned for DSM model, and on the right, only the ground returns for the DTM model. The final P-wave velocity model was also calibrated with real field velocity data from upholes or near weathering surveys coming from the seismic reflection campaign to finally obtain the most real P-wave velocities magnitudes around the study area. The final P-wave velocity model around the pipeline, calibrated to the upholes, is shown as a plan view at the right of the slide. Two different zones of P-wave velocities behavior are identified, a higher and a lower velocity zone. The vertical section A to A also shows a change in this behavior. Field geology information acquired in the area shows that velocity zones discrimination correlates very well with two different lithological formations. The Nereyra formation, composed mainly of clay material with intercalations on sandstones, the Ipururo formation, which is a sandy formation with clay intercalations, and Based on this information, we should say that this is the first indication that P-wave velocities are a result of the geological behavior of the soil. Now we are going to pass into the second part of the study, that is the creation of the predicted geological maps. The next step in this study was to build the predicted geological maps based on the P-wave velocity model and geology of the area. Several predictive geological maps were generated, like the lithological or soil type, distance to a geological fault, depth of the strata or soil thickness, etc., which were finally correlated to each other to predict areas with greater or lesser ground stability. Each predicted map will be considered as a factor that will influence the delimitation of areas with higher or lower stability risk. In this presentation, we will show you the most important ones for the area of interest. The first map is the lithology prediction map. In the green and yellow zone, we are going to see the zones of high velocity, and they are going to represent the silty clay soil zones. The gray colored zone is the zone of low velocity values that represents zones of silty sand soils. This predictive map, for example, shows a high corresponds with the lithology described in the surface geological maps, as well as with the lithological samples described directly in the field. The second map is the strata depth prediction map. If we have less than 15 degrees of inclination, they are going to be located into the blue color zone. Inclinations between 16 degrees and 25 degrees are going to be located into the green color zone. Inclinations between 26 degrees to 35 degrees are going to be located into the yellow color zone. And inclinations higher than 36 degrees are going to be located into the red color zone. The lower the degree of inclination of the stratification, the greater the stability of the slope. The third map is the slope and stratification parallelism prediction map. If we have a parallelism, an angle formed between the slope and stratification of more than 30 degrees, they are going to be located into the blue color zone. If this angle is between 11 to 20 degrees, they are going to be located into the green color zone. And if the angle is less than 10 degrees, they are going to be colored by red, okay? The smaller the angle formed between the inclination of the strata and the inclination of the slope, the greater the risk of a landslide. The fourth map is the distance to a major fault prediction map. If your pipeline is between 0 to 200 meters away from a fault, is going to be colored by red. If your pipeline is between 200 to 500 meters away from fault, is going to be colored by yellow. If your pipeline is from 500 meters to 1 kilometer away from a fault, it's going to be colored by green. And if our pipeline is more than 1 kilometer away from a fault, it's going to be colored by blue or light blue. Okay, and what's important here? That if the pipeline is located in an area where there is a geological fault, the density of fractures around it will be higher, and therefore the risk of a landslide will be higher too. The fifth map is the topography depth prediction map. If we have a topography depth less than 25 degrees, it means that they are low dips. They are going to be identified by the blue color zones. If we have dips between 26 to 35 degrees, I mean intermediate dips, they are going to be identified by a yellow color zone. And if we have dips of more than 36 degrees, it means high dips, they are going to be identified by the red color zones. What is important here? That the lowest slope zones reflect areas where the strata have not undergone considerable deformation, while the highest slope zones contribute to the risk of a landslide compromising the integrity of the pipeline. And the last map is the sediment thickness prediction map. If we have less than 10 meters thick of sediments, they are going to be identified by the blue color zones. If we have between 11 to 15 meters thick of sediments, they are going to be identified in the green color zone. If we have between 16 to 20 meters thick, they are going to be located into the yellow color zones. And if we have over 20 meters thick of sediments, they are going to be colored by red. The important thing here is that a high amount of sediments increases the weight of the slope, making it unstable, increasing the volume of soil that can be displaced around the pipeline. Then we are going, after finishing the creation of the several predictive maps, we are going to pass into the results validation. Before obtaining the final right-of-way risk map of the U200 pipeline, factor maps were validated with geological and geotechnical information obtained in the field during pipeline maintenance operations, okay, done between the years 2014 to 2021. The first validation shows that field data, which is marked as DDB control points here, have a high correlation with a category or weight assigned to the terrain morphometry or topography map. This results in a 90% correlation between both results, okay? The second validation, towards the right of the slide, shows that the field data, also marked as DDB control points in the image, okay, have a high correlation with the category or weight assigned to the lithology map. This results in a 95% correlation between both results. The final part of this study is the 3D risk evaluation. Each predictive factor is assigned a weight in order to evaluate the general risk of the area around the pipeline in a quantitative manner. Once the validation and correction of all relevant factors like lithological, structural, topographic, hydrological, and seismic factors was completed, the final risk map was constructed using the following formula. This formula correlates the lithological, structural, topographic, hydrological, and seismic factors that we have done in the previous steps. The final risk map was also validated with a risk identification defined by the operations of maintenance in 2020 as part of the pipeline's maintenance activities. Both results classify the risk in three zones, okay? The first zone, which is a low risk zone colored in green, where the soil is not prone to landslides. A moderate risk zone colored in yellow, which is considered an intermediate zone, and a higher risk zone colored in orange, where the soil instability increases the risk of landslides. What are the conclusions of this study? First, it is demonstrated that with the new 3D seismic refraction technique, it is possible to evaluate and define geodynamic hazard zones with a high degree of certainty, more or less 90%. Second one, that three-dimensional model of P-wave velocities generated with the seismic refraction technique shows that the waves respond not only to lithological factors, but also to structural and many other geodynamic factors to which the ground is exposed. 3. Risk prediction maps should be generated from the analysis and interpretation of the P-wave velocity model, but they should always be validated with geological information of the area, LIDAR DTM topographic information, different hydrological and seismic studies, and periodic field inspections. And 4, the risk zoning concludes with the delimitation of areas exposed to greater or lesser probability of a landslide occurrence that would potentially affect the integrity of the U200 right-of-way pipeline, identifying those areas that require immediate or future attention. Our contributions and recommendations are, first, we obtained the necessary data for the development of the project, seismic refractions, from previously acquired reflection seismic information. Therefore, we don't need to reinvest money to acquire new data. The aerial distribution of the reflection seismic is much larger than the one obtained by a conventional two-dimensional refraction seismic, and this contributes to have more data to evaluate the risk of almost 15 kilometers of the right-of-way of the U200 pipeline in a three-dimensional and more optimized way. 3. Predictive lithology, structural topography, etc. maps will allow to define the improvements to be applied into the right-of-way of the pipeline maintenance stage. According to the type of soil, for example, we could select the best engineering task to be done in points where landslides occur or will occur. 4. Apply the results obtained in this project as base information for the design of new pipeline projects. Having this aerial and detailed characterization of the area is one of the determining factors for the design of new pipelines to avoid future unnecessary or unwanted maintenance costs. And the last one recommendation is that this technique also make it possible to identify the areas with the lowest geological and geotechnical risk to establish the new loops of any pre-existing pipeline. Thank you so much